And hello, welcome back. We'll just pick up where we left off. Okay, so in the last video we were dealing with the Navier-Stokes equations. I was trying to explain why, even though the fluid is compressible, in a sense that as temperature changes, your density changes. So there's a little bit of compression here, and expansion, of course, or contraction and expansion. Why are we still using the incompressible form of the Navier-Stokes equations? So I explained by saying, okay, firstly we say that all the terms that we expand out when we do the mass balance and everything, okay, these are very small. These changes are very small in comparison with the other terms. So for example, in the mass balance equation, u del rho del x plus rho del u del x, this is what it is. But this term, u del rho del x, is actually small compared with rho del u del x. So this is why we kind of just ignore the first term and we just use the incompressible form of the Navier-Stokes equations. And then I went on to say that we will try to assume 2D, as we do with most boundary layer equations, and we'll just drop off GZ. Okay, so we drop off W equals to 0 everywhere, so all these terms will drop off. GZ equals to 0. Why? Well, yeah, of course it's 2D flow. So this is what we are dealing with. We have a hot fluid surface. We have a hot fluid surface here. We have a T infinity. And then this is in the positive y direction. Of course, then where must gravity be going? It is over here. G must be in the negative y direction. Okay, so that means Gx and Gz, the gravity components in the x and z direction, are all 0. Okay, so that's why Gz here is 0. Okay, so we'll apply the same logic for the x and y velocity, or more rightly put, momentum equations. Okay, so let me uncomment this and we'll go. Alright, so firstly we get rid of the w velocity, the z velocity, so w actually drops out. And not only that, we assume that there's no variation of u or v in the no variation of u and v in z direction. So these are the assumptions that we are putting in, so that we can just cancel off this del 2u del z terms. Okay, so del by del z terms are all dropped out. Okay, so gravity is only in the y direction. So gx equals to 0. Gy, I can just leave it there. Of course, gy we can just substitute minus g into this equation here, but we'll do that later. Okay, and last but not least, the steady state assumption will just help you to get rid of these del by del t terms. Okay, this del by del t terms are over here. We'll disappear them because we want our boundary layer equations. We by default assume steady state. Thus, we will have now our hydrodynamic equations to begin with. Okay, so these are our hydrodynamic equations. Okay, so this is the one where I took out the steady state stuff. So that's one set of equations. We have continuity here, which we will just use the standard del u del x plus del v del y equals to 0. Okay, maybe I'll just copy and paste. Okay, maybe not. It's kind of repetitive. Okay. Next thing is we need to do is energy balance. Okay, this is energy balance. So what's in our energy balance? Okay, we likewise for energy balance, we assume that the compressibility effects here are like minimal. Okay, the compressibility effects here are minimal, and you can just take and average the conductivity, thermal conductivity, heat capacity, density. All of these are contained within the alpha term, so that you can have this nice neat Laplacian type equation. Okay, so these are for fluids with not very much varying properties, or at least not highly varying alpha or conductivity for that matter, because you kind of need to get rho Cp from the advection terms over here. Yeah. Okay, so long story short, we assume temperature doesn't vary in the z direction, so I just cancel these two terms off, and we assume steady state. These are all you need. Okay, and of course no heat generation terms as well, no significant heat generation terms in this equation. We assume that they are small in comparison to the conduction, which is these terms here, the Laplacian that you see here, and this is the advection. So what this equation here is saying, okay, what this equation here is saying is that the advection terms balance out with the conduction terms in the fluid. So that's pretty standard. Okay. So earlier I talked about something called the Boussinesq approximation. Okay, why do we need to talk about that? All right. So as with every boundary layer equation, we want to drop off more terms in the boundary layer. So we know not all terms in the boundary layer equation are actually significant. So we'll do some scaling analysis to find out which equations we can drop off, which terms we can drop off further from our Navier-Stokes equations. So that's what we are doing here. Okay, Boussinesq approximation actually comes by us asking this question. Why does the buoyancy force come from in these equations? Where's the buoyancy force coming from, or represented in these boundary layer equations? So okay, over here we have 1 over rho naught del P del Y, and then Gy. Okay, we know that buoyancy comes around because of gravity, right? There's a relative density change due to gravity. Okay, our gravity terms are actually contained in Gy here. So that's the force actually pushing the liquid down. So what actually pushes the liquid up? Okay, it's actually the surrounding pressure. Okay, it's the surrounding pressure. Okay, the surrounding pressure. In fact, the pressure at the bottom, okay, the pressure at the bottom is greater than the pressure on top. Okay, it's pressure at the bottom. Maybe this is P at Y, and this is Py plus delta Y. Okay, is greater than the pressure on top. Okay, pressure at the bottom is greater than pressure on top. So what this is saying is del P del X, or del P del Y this time, no more del P del X. There is a negative pressure gradient that's pushing this fluid upwards. Okay, so what does it mean? As Y increases, the pressure decreases. So del P del Y less than 0. This is actually the buoyancy force pushing the liquid outwards. Now normally in our force convection, the buoyancy forces and the gravity forces will balance out. Okay, in this case, definitely not the case. So that's what your buoyancy forces will come from this del P del Y term. Okay, so how do we actually put this all in math? Our mathematical equation form. Okay, like I said, the buoyancy force comes from this del P del Y term. Okay, so again, this buoyancy comes from surrounding fluid of heavier density pushing the lighter fluid upwards. Okay, it should come from the pressure term, but how do we do it? Okay, so how do we do it? How do we include this change in density to be inside our pressure term? Because that's where the buoyancy comes from, and we know cold fluid sinks, hot fluid rises relatively in a natural convection case. So over here we don't really see this density being put explicitly into this pressure term. Right? Density is not explicitly put into this pressure term. How then do we include it? Okay, so the way we go and put density into this pressure term is by considering the following. Okay, hydrostatic pressure equals to H rho G. Okay, so I already put the yes, I think yeah, I put the expression here. Okay, anyway, I think where was I kind of lost track. I think I lost track. Oops. Okay, anyway, I wanted to get an expression for pressure in terms of density so that we can relate it. Okay, so okay, we don't exactly know what pressure pressure everywhere in the boundary layer is. Okay, we don't know what the pressure is here, what the pressure is here, etc., etc., because that will actually require you to okay, let's say at this point, right, you need to kind of think of you need to integrate, okay, because pressure equals to rho GH. Okay, yeah, so you need to integrate all these small pressures on top all the way up, because the density may change, so the pressure on top may sort of change as well. Okay, so thing is this, we are not quite sure how this pressure will change from time to time. Okay, at least inside the boundary layer. Okay, so yeah, we can't use the rho GH trick inside the boundary layer. It's not as clear how to do it. Okay, so how do we work around this? Okay, let's think about what we do know. Okay, we know the pressure over here. Okay, what's the pressure over here? Okay, so this one is very simple in the free stream, right? At this point in the free stream, it's a rho GH kind of formula. You don't need any kind of integration or anything. So we can call this the free stream pressure P infinity goes to rho G. Okay, rho G, rho GH. Okay, this G is of course the same as this. Okay, again I have not replaced the GY with minus G yet. So yeah, try not to get confused. GY is just the component of the body force or gravitational force in the y direction. So in this case, body forces are just gravitational forces. There are no other body forces acting on this thing. Okay, so what is rho and g? This rho will be actually the free stream. Okay, free stream. What do you call that? Okay, that will be actually the free stream density. Okay, free stream density. G is just G. H is this whole distance here, all the way from the top, wherever the top is. So where is this top? All right, where is this top? So let's say your whole wall is length L. Okay, your whole wall all the way through is length L. So technically this L can actually just extend to infinity, which I don't know, how would you think of that? Maybe there's a finite wall or something, but at least for this boundary layer we don't really care too much. Just take it as if there's this wall with a length L, and then if you want to calculate this height, you have to take this L and then you need to subtract this length. This is something you do know. So this length is just h. Okay, this length here is h. So this height here we want is actually, okay, we want to have this L minus h. So this is what the P infinity is, pressure at infinity. Okay, so what's the use of this? Okay, well, one assumption we can make is that, okay, dP dy at the boundary layer equals to dp dy, okay, and the free stream, which I will just use the infinity sign here to denote that. Okay, again, dp dy, the boundary layer, equals to dp dy in the free stream. Okay, does this work? Okay, so this is the assumption we will be using, but let's think about it for a while. Okay, if this were not true, what will happen? Okay, if let's say the pressure gradient, let's say the pressure, okay, let's say we start at this point, or we start at this point. Okay, we have barely so-called met the wall yet, quote unquote. So pressure here and pressure here is the same. And if you go just a little bit up over here and just a little bit up here in the boundary layer. Okay, maybe I'll just draw it a little bit off center. Okay, so if this dp dy is, let's say, okay, this is the standard reference, right? So this is dp dy in the free stream. Alright, so you have a pressure at 0 here. Then maybe we call it P1, pressure at 1. dp dy is actually determined by the difference between the P1 and P0. Okay, and let's say the pressure at this point is also P0. It's also in the free stream. And if you kind of move up a little bit, okay, into the boundary layer, so the convection started, let's call this pressure P2. Okay, if by some intuitive reasoning we say that the fluid here is hotter, therefore the density of the fluid above here is less, so to speak, what do we expect? Okay, we expect the hydrostatic pressure to be less, right? So we expect P1 to sort of be greater than P2 if P0 and P0 is the same, right? What will happen if P1 is greater than P2? Okay, if P1 is greater than P2, you will actually have fluid flowing in from the free stream into this area here, which is exactly what we expect. You know, when fluid flows upward, there should be, I mean, in a natural convection, the fluid will flow from the cold region into the hot region, into the wall, so that as fluid leaves the hot region, fluid from the cold region will, fresh fluid from the cold region will come in to displace that. So when fluid flows from this free stream region to the P2 region, what happens? Okay, so more or less, after a while, you should expect that the P2 should equal to P1 when you kind of equilibrate everything properly. Okay, so you give it some time to settle the flow patterns and everything, and the natural convection thing. We should find that P1 is equal to P2, the so-called hydrostatic wise, you know. Okay, why? Because some of this pressure, P1 pressure, is being converted into like kinetic energy so that it can push the fluid from the free stream into the what do you call that, boundary layer. I mean, that's one way you can think about it. Hope is the right explanation, but that's how I like to think about it. So there's pressure, excess pressure here, which pushes fluid into here. So the energy has to come from somewhere. So that comes from a drop in this P1. Okay, P1 will drop so that fluid can flow from the free stream into this boundary layer region. So of course, ideally in the free stream, the velocities in the x and y component would be 0, but it's not exactly, strictly speaking, 0. Okay, it's not completely 0. There should be some fluid movement, but it's negligible. Okay, compared to, let's say, all the fluid movement here in the boundary layer region. Okay, so I've said my piece, and what I want to say is that the assumption we make is that dp dy in the boundary layer equals to dp dy in the free stream, more to the free stream side. Not all the way out, but just enough in the free stream so that we can use this rho GH assumption kind of a thing. Okay, give or take. Alright, so that's the assumption we will use. Okay, so that we can get this dp dy. Okay, so that's how we get this rho infinity L minus y, p infinity equals to L minus y, rho infinity minus gy. Okay, minus gy is just g. Okay, because gy is minus g. Okay, I have yet to replace the gy here with minus g, so that's why I use this thing here. And why do I use the y coordinate here rather than h? I mean, it's kind of interchangeable, but let's see. Let's go back. Yeah. And let me clear the board. It's so messy. Oh my goodness. Okay. Alright. Let's have our boundary layer plume. Okay, so the length here is what we call h, the height of the wall. Okay, so we also like to call this, how far in y we are going in. Okay, they're basically the same, but it makes differentiation a little bit easier if you use y. Okay, so remember the height here, the pressure of the height here is equals to this wall length L minus y. Whatever the wall length is, we don't really care, because we are not interested in the absolute pressure, but rather the pressure gradient. Okay, why do we want the pressure gradient? So that we can substitute this term in. So we have a dp infinity dy, okay, equals to minus rho infinity minus gy, or in other words, minus rho infinity g. Okay, so we need to substitute this back, and we will get the following. Okay, so we substitute this back. Okay, so we substitute all of this back here, dp dy, which is just minus rho infinity g. So we just substitute this here. Okay, and yeah, that's it. Okay, so over here I used it in terms of gy, but of course we need to swap it out. Gy equals to minus g, as I said before, and then we can get minus 1 over rho minus rho infinity g minus g. Remember this rho over here, rho naught, is the density in the boundary layer. Rho infinity here is the density in the free stream. Okay, so now what other thing are we saying? Okay, what other thing are we saying? Are we implicitly saying when the dp infinity dy in the free stream is equals to dp dy in the boundary layer? It means that there is no variation of this pressure gradient with x, or no variation of pressure with x, this static pressure. Okay, so this term here, we can kind of just disappear the term. That's not an issue. Okay, so this term here disappears. Okay, so I'll stop for now. We'll continue on. But what I'll say is, we can just multiply throughout by rho naught, but the term rho naught kind of implies that it's a fixed density. So I'm going to replace everywhere I see rho naught, I'm going to replace it by just rho, which is the density in the boundary layer. So that's why you will see me using rho instead of rho naught over here, which is the so-called average fluid density, so in the boundary layer. Okay, so we're going to use rho. We're going to use rho to denote that it's the average fluid density in the boundary layer rather than rho naught. Okay, so that actually depends on the film temperature, and it is independent of x and y, because film temperature is T infinity plus T surface divided by 2. Okay, it's both of them added together, then you divide by 2. Anyway, I'll stop talking now. I'll see you in the next video.